Let's look at the first order linear differential equation. dy dx plus p of x times y is equal to q of x. Furthermore now, let's suppose that y1 is a solution to the homogeneous differential equation. This, of course, means that dy1 dx plus py1 has to be 0. Now, since this is linear, there is only one solution. So the general solution is given by C1 times Y1. The technique of variation of parameters involves finding a particular solution of the form u1 of x times y1 of x. And of course, this would be a particular solution to the non-homogeneous differential equation. So what we're going to do is we're going to take this, we're going to plug this back into here. So d dx of u1 y1 plus p times u1 y1 has to equal q. Taking this derivative, remember both u1 and y1 are functions of x, that's a product rule. So we'll get u1 dy1 dx plus y1 times du1 dx plus p u1 y1 is equal to q. Now let's group our u1 terms together. So u1 times dy1 dx plus py1, now plus y1 du1 dx is equal to q. This right here, though, is equal to 0. Right? That's right up here, because y1 is a solution to the homogeneous linear differential equation. So we're left with y1 du1 dx has to equal q, which means that du1 dx is q over y1. Now that's separable. So du1 is q over y1 dx. And so u1 is the integral of q over y1 dx. So this is our u1. Therefore, our particular solution is y1 of x times the integral q of x over y1 of x dx. Now, remember, when we studied the linear first order differential equations, we would find that y1 would be of the form e to the negative integral p of x dx. So if we use this, we can write yp is e to the negative integral p of x dx times the integral q of x over e to the negative integral p of x dx, or as e to the negative integral p of x dx times the integral of e to the integral p of x dx times q of x dx. Let us now consider a second order linear differential equation in standard form. I'm going to use f of x instead of g of x, my apologies. Now we can easily find the complementary solution by using the techniques we studied a couple lessons ago. We now need to find a particular solution. So what we'll do is we're going to guess that the particular solution will have the form y of p is equal to u1 of x times y1 of x plus u2 of x times y2 of x. So we'll find that y prime is u1 y1 prime plus u1 prime y1 plus u2 y2 prime plus u2 prime y2. The second derivative would be u1 y1 double prime plus u1 prime y1 prime plus u1 double prime y1 plus u1 prime y1 prime plus u2 y2 double prime plus u2 prime y2 prime plus u2 y2 double prime, u2 double prime y2 plus u2 prime y2 prime, and this simplifies to u1 y1 double prime plus 2 u1 prime y1 prime plus u1 double prime y1 plus u2 y2 double prime plus 2 u2 prime y2 prime plus u2 double prime y2. So now we're going to plug all this back into the differential equation. So there's y double prime There's p times y prime. There's q times y, and this has to equal f of x So let's try and group all of our u1 terms together, all of our u2 terms together. So what do we get? We'll get u1 times y1 double prime plus p y1 prime plus q plus u2 times y2 double prime plus p y2 prime plus q. Now we're going to have plus y1 u1 double prime plus, I will now separate the two u1 prime y1 prime and the two u2 prime y2 prime into two separate terms. So instead of writing 2 u1 prime y, I'll write u1 prime y1 prime plus y2 u2 double prime plus u2 prime y2 prime. And there's a reason for that. Plus p times y1 u1 prime plus y2 u2 prime plus u1 prime y1 prime plus u2 prime y2 prime. Of course, this still equals f of x. Now, these two terms are both 0 because y1 and y2 are solutions to the homogeneous differential equation. This term right here, as well as this term right here, are derivatives of products. Specifically, this is the derivative of u1 prime y1, and this is the derivative of u2 prime y2. So we can now rewrite this as d dx of u1 prime y1 plus d dx of u2 prime y2 plus p y1 u1 prime plus y2 u2 prime plus u1 prime y1 prime plus u2 prime y2 prime. And then using the sum rule of derivatives, we can write this as a single derivative, u1 prime y1 plus u2 prime y2. And of course, that whole thing will have to equal f of x. Now we're seeking two functions. We're seeking a u1 and a u2. So it would seem reasonable that we would need two equations. Well, if we suppose that u1 prime y1 plus u2 prime y2 has to be 0. Then we have u1 prime y1 prime plus u2 prime y2 prime has to be f of x. This gives us a system of two equations and two unknowns. We will be using Cramer's rule, which is studied in a typical linear algebra course. This will give us that u1 prime will have to be w1 over w, u2 prime will have to be w2 over w, where w is the Wronskian of y1 and y2, and wi is the determinant of the matrix obtained by replacing column I in W with 0 f of x. We can then determine u1 and u2 by integrating u1 prime and u2 prime respectively. So we will actually look at a couple examples next to show how this process works out. Let us look at the differential equation. Y double prime plus y is equal to tangent of x. So we first need to find the complementary function. So we need to solve y double prime plus y is equal to 0. So the auxiliary equation is m squared plus 1 is equal to 0, which leads to m being plus or minus I. So our complementary would be c1 cosine of x plus c2 sine of x. Now on to finding yp. So our function f of x is tan x. We now need the Wronskian of y1, y2. So it's the determinant of cosine x, sine x, and then negative sine x, cosine x. So we have cosine squared plus sine squared, and that is, of course, 1. W1 is the determinant. We replace column 1 here with 0 f of x. And then column 2 remains unchanged. So this becomes negative sine x tan x. W2 is a determinant. We'll replace column 2 here with 0 tan x. And then column 1 remains the same. So here we get cosine x times tangent x. And since tangent is sine over cosine, this is simply sine. So u1 prime would be negative sine x tangent x, and u2 prime would be sine of x. So u1 is the integral of negative sine of x tangent of x, which is sine of x minus the natural log of the absolute value of secant x plus tangent x. u2 is the integral of sine of x dx, which is negative cosine of x. This means that y sub p is y1 times u1 plus y2 times u2. We have a cosine times sine, cosine times negative sine. Those are going to drop out, and we're left with negative cosine of x times the log of secant x plus tangent x. So our general solution is the complementary plus the particular, c1 cosine plus c2 sine minus cosine times the log of secant plus tangent. Okay. Let's now look at the differential equation. Y double prime minus y is equal to 1 over x. So complementary, we need to find the solution to y double prime minus y equals 0. This is m squared minus 1 equals 0, which gives m as plus or minus 1. y1 would then be e to the x, y2 e to the minus x. So the complementary function is c1 e to the x plus c2 e to the minus x. To find yp, we make note that f of x is 1 over x. So w is the determinant of e to the x, e to the minus x, e to the x minus e to the minus x. So it's negative 1 minus 1, which is negative 2. W1, first column is now 0, 1 over x. Second column remains unchanged. So this is negative e to the minus x over x. W2, the first column, remains unchanged. And the second column becomes 0, 1 over x. And this gives e to the x over x. So u1 prime is e to the minus x over 2x. u2 prime is negative e to the x over 2x. This, of course, means that u1 is the integral of e to the minus x over 2x. u2 is the integral of negative e to the x over 2x. Now these are non-elementary, right? We cannot find an antiderivative. So we will write these as integral defined functions. That is, we will say that u1 is a half the integral from x naught to x, where x naught is some constant, e to the minus x over x. u2 is negative a half integral from x naught to x. I'm sorry, in the first one, while you can use the same variable, it's standard not to. So I'm going to write it as e to the minus t over t dt, and then e to the t over t dt. This gives us a particular function, y1 times u1. So we get e to the x over 2 times the integral x naught to x of e to the minus t over t dt, plus y2 u2, so minus e to the minus x over 2 times the integral from x naught to x of e to the t over t dt. And we would write our general solution then as y of x is c1 e to the x plus c2 e to the minus x plus e to the x over 2 times the integral x naught to x of e to the minus t over t dt minus e to the minus x over 2 times the integral from x naught to x of e to the t over t dt. And this would be our general solution. We can generalize the previous discussion to an nth order linear. In this case, our complementary function will have the form c1y1 plus c2y2 plus yada yada plus cn yn, so we'll have n solutions. We can then form a particular function in the form of y1 u1 plus y2 u2 plus so on and so forth plus yn un, where ui prime is given by w over wi. In this case, w is still the Wronskian, so it'd be y1, y2 through yn, y1 prime, y2 prime through yn prime, until we get to y, the n minus first derivative of y1 the n minus first derivative of y2, and then the n minus first derivative of yn. That determinant. And wi is found by replacing the ith column in W with 0, 0, all the way down to f of x. So, for example, if this was a fourth order differential equation, we would have 4 y's. So we'd have a u1, u2, u3, u4, where ui prime was w over wi. So you'd have 4 of these w sub i's. Your w would be a 4x4 matrix, going down to the third derivative. Then each wi would be found by replacing each of the 4 columns with 0, 0, 0 f of x. The fourth entry would always be your f of x. Everything else would be 0. So your last entry in wi is always f of x. Everything above it will always be 0. So w1 would be found replacing this column with 0, 0, 0, 0, blah, 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 f of x. w2 would be replace this column, so on and so forth. That is variation of parameters. This has an advantage over the undetermined coefficients in the sense that we made no restriction on the form of f of x. Remember, to use undetermined coefficient, there was a restriction on this f of x. The f of x had to be of a particular form. Variation of parameter has no such restrictions. However, it can be a bit more of a pain depending on the order and what you get out of the w's. That concludes this lesson. I hope you've learned something, and we'll see you in the next one.